To the Sports Vis session. My name is Johanna Schmidt. I'm your session chair for today. I'm from the IEEE Vis Research Center in Austria, and I'm going to guide you through the Sports Vis session. We have 3 in-person talks today and 3 virtual talks. And our first talk is going to be about augmented sports videos using natural language. And the talk is going to be presented by Tzu-Tian Chen. So you already set up your laptop, seems to work fine. So actually, the floor is yours.
Thank you. Thanks for the introduction. Good day, my friends. I'm Tzu-Tian Chen from Harvard University. Today, I will talk about Sportthesia, augmenting sports videos using natural language. I would like to thank my awesome collaborators, and this work won't be possible without their helps. All right, let's get started. Augmented sports videos combines visualizations and video effects to present data in videos. Because these videos explain complex insight in an engaging way, they have become increasingly popular in recent years. For example, TV companies and sports organizations use augmented sports videos to engage viewers, provide extra insights for fans, and help experts communicate analytical findings to billions of enthusiasts around the world. However, creating augmented videos remains a difficult task. Existing augmented tools usually have complex user interface and are designed for expert video editors. Users have to manually draw the graphical marks in the video to represent the data and navigate the video's timeline by switching back and forth, which is time-consuming and tedious. On the other hand, sports insights are usually communicated using natural language, such as in commentary, presentation, and articles. But purely verbal descriptions lack visual cues. This motivates us to think about if we can enable users to directly use their insights in natural language to create augmented videos. We explore these questions and present Sportthesia, a text-to-visual system that takes raw video footage and textual comments of rugby-based sports as input and output augmented videos. Sportthesia leverages a set of computer vision and natural language processing models to achieve this goal. It's a technique that can be employed in different application scenarios. For example, we have integrated Sportthesia into a video authoring tool to demonstrate how it can facilitate augmentation of a tennis match video. Let's first take a look at this demo. So the authoring tool consists of a video view and a timeline. Users can brush on the timeline to add their text comment. A basic feature of Sportthesia is to highlight video objects. For example, by typing Federer, the system will highlight the player in the video. The user can also try other descriptions, such as Djokovic, or Roger, the first name, or even Federer's opponent.
Federer's opponent.
The user can also highlight places in the video by typing, for example, forehand court,
Forehand court.
or service court,
Service court.
or Federer's forehand court.
Federer's forehand court.
In addition to highlighting objects, Sportthesia allows users to visualize actions. For example, the user can type, Federer is running,
Federer is running.
or Djokovic is hitting.
Djokovic is hitting.
The system will visualize the data generated by these actions in the video. Moreover, Sportthesia supports the visualization of data and emotional cues. By combining these 4 categories of entities, users can visualize more complex insights. Let's take a look at this example. Federer looks to be covering the cross court and gets him close to the backhand court.
Federer looks to be covering the cross court, gets him close to the backhand court.
The user may mention other places in the court, such as the net.
Federer looks to be covering the cross court, gets him close to the net.
Sport teacher will faithfully visualize the information in the video. Users can comment on multiple periods of the video to create more complex augmentations. For example, the user first comments that Federer was carrying another shot to his backhand.
Federer was covering another shot to his backhand.
Then the user comments on the following event that he was in the backhand court and has to cover too much distance.
He was in the backhand court and has to cover too much distance.
Here, sport teacher can correctly understand he refers to Federer in the first sentence. And finally, the user can play these two augment clips together to tell a complete story.
Federer was covering another shot to his backhand. He was in the backhand court and has to cover too much distance.
In addition to offering tools, sport teacher can also be used to augment videos by using the video's auditory commentary. Let's first take a look at this example.
Hallett now reaching the low ball, scoops the backhand just inside the baseline. Williams cross-court. Hallett down the line with a forehand. This is brilliant from Hallett. Now running onto a backhand and cross-court for the winner.
To augment these videos, we separate the audio track from the video and convert the audio into text. We then load the text and video into Sport Teacher and automatically generate the augmented video.
Hallett now reaching the low ball, scoops the backhand just inside the baseline. Williams cross-court. Hallett down the line with a forehand. This is brilliant from Hallett. Now running onto a backhand and going cross-court for the winner.
Let's take a look at another demo of table tennis.
Oh, surprise. Ma Long looks like he's going cross-court and changes it up for the parallel.
So behind these applications and demos, Sport Teacher implements a three-step approach. First, it detects the visualizable entities in the commentary. Then, it maps the entity to embed the visualizations. And finally, it schedules the visualizations to play with the video. And by composing the visualizations with the raw footage, Sport Teacher output the argument videos. And to achieve these three steps, we need to answer three questions. First, what kinds of text entities need to be detected? Second, how to visualize these entities? And third, how to schedule these visualizations to play with the video. To answer these three questions, we conduct a formative study, and based on the findings, we develop Sport Teacher, which uses computer vision models to detect video objects and natural language processing models to detect text entities. And we connect them based on some rule-based methods. And for more details of the formative study and the technical implementations, please check our paper or talk to me offline. And to evaluate Sport Teacher, we conduct a technical evaluation and an expert user study. In the technical evaluation, we manually annotate the visualizable entities in the commentaries of 155 video clips and use the annotated dataset to evaluate the accuracy of the entity detector. We achieve a good performance of an F1 score of 0.9 and also discuss the failure cases which can be improved in the future. And in the expert evaluation, we invite 8 experts and ask them to finish several creation tasks using Sport Teacher, and their feedback confirmed the utility, effectiveness, and high certification of our language-driven creation method. And please check our paper for the details of the evaluation and findings. So in summary, Sport Teacher significantly simplified the creation process of augmented sport videos by directly using insights expressed in natural language. and opens up a wide range of applications from presenting and discussing game tactics in team meetings to improving the live game viewing experience. And this is all for today, and I'm happy to take questions.
Thank you very much for your talk. We are looking forward to questions on Slido or on Discord. In the meantime, I have one question regarding the player identification. How did you identify the players in the video? Because they also switch sides and so on.
Yeah, that's a good question. So currently, we use some rule-based method to identify the players. For example, we can use the computer vision model to detect which player is far from the camera, which player is near the camera, and then we have some meta information to help the system understand who is who. Yeah.
Thank you very much. And another question from Slido. Can you give some examples or things that cannot be visualized with natural language processing?
Yeah, so based on our formative study, we currently identify 4 categories of entities that can be visualized in the video. And there are other entities that we currently think that should not be visualized in the video. And most of the failure cases in our study is due to the uncertainty of the commentary, because sometimes the natural language processing model cannot totally understand what humans are speaking. But we think that our technique can be used as a fast prototyping tool to create a draft very quickly. And then we also provide some user interface to allow the user to refine the result of the user.
Thank you very much. Let's thank our speaker again. Thank you. And we move on to our next talk. The next talk is going to be a pre-recorded video, and it's called OB Tracker, Visual Analytics of Off-Ball Movements in Basketball. The talk is given by Yihong Wu.
Hello everyone, I'm Yihong from Zhejiang University. Today I'm glad to introduce our paper, OB Tracker, Visual Analytics of Off-Ball Movements in Basketball. In basketball, off-ball movement is one of the most common actions of players. Although not having the ball in hand, the off-ball players can still effectively contribute to the offense. For example, they can make a sudden move to get rid of defenders and create an opportunity for an open shot. Hence, professional basketball teams place great importance on off-ball movement analysis, as it can help find high-performing players and build effective strategies. Existing studies of off-ball movement analysis can be broadly divided into 2 categories. The first is event-based methods, which incorporate match statistics and events to explore the effects of off-ball movements. However, the special patterns of off-ball movements are seldom included in these works. Thanks to fine-grained tracking data, special-based methods are introduced. For example, some researchers aggregated player trajectories to identify a team's offensive structures. Deep learning models are also introduced to assess the value of off-ball movements. Although useful, the deep learning features are often insufficiently interpretable. This somewhat affects the confidence of sport experts in the model results. Visualization methods have also been widely applied in basketball analysis. However, these works are mainly based on box score statistics and play-by-play data. Comprehensive visualization for off-ball movement is still absent. To help coaches perform an in-depth analysis of off-ball movements, we designed OB Tracker, in which users can review a team's typical off-ball movement patterns, compare the performance of different players, and understand the detailed process of an off-ball movement. We face 3 main challenges when developing OB Tracker. First, the values of off-ball movements are hard to detect, since common basketball statistics such as points and assists are mostly result-oriented. The assessment of off-ball movements thus requires a full investigation of the overwhelming on-court information. Second, the aggregation of off-ball movements should preserve related game context. For example, coaches would like to learn how often a specific type of off-ball movement is used at crucial moments. Third, due to the constantly changing player locations, experts require to check the progression of an off-ball movement. How to visualize the dynamic process remains to be resolved. To solve the first challenge, we use a public tracking dataset from SportView and propose an interpretable model to assess the value of off-ball movement. With the data, we further assign the roles to different players, including the ball handler, the screener, and the cutter. The cutter's actions are the main focus of our study. Inspired by previous works, we assess the value of an off-ball movement by the improvements it makes to the offensive team's scoring chances. To model the scoring expectations, we worked closely with our domain experts and obtained a two-step process. The first step is calculating the shooting expectation, which estimates an off-ball player's scoring expectation assuming she or he receives the ball at the current time. For example, we take the player locations at time t as inputs and divide the basketball court into grids. Based on the grids, we further build three matrices to represent the off-ball player's dominant area, the defense she or he faces, and the shooting performance across the court. The shooting expectation is then obtained from an element-wise matrix multiplication. The second step is calculating the passing probability, which estimates the probability of an off-ball player receiving the ball based on the player locations and ball locations. This prediction task is done by linear regression. For the latter two challenges, we invited 4 experts and derived the 3-level requirements for off-ball movement analysis, including team-level summarization, player-level investigation, and action-level explanation. For team level, the summary view is designed to give experts an overall picture of a team's typical off-ball movement patterns. The list on the left shows how often and how effectively each team uses off-ball movement. Users can select a team of interest and view its most commonly used off-ball movement on the right. All the trajectories shown are aggregation results, which are obtained from a sequence of subdivisions. To describe the features of different off-ball movements, we designed a glyph to represent a specific type of off-ball movement. The XY coordinates encode the frequency and effectiveness. To incorporate the game context, we add 2 histograms to show how a type of off-ball movement distributes over the score difference and the remaining game time. Then, users can select a type of off-ball movement for further analysis. In the player view, users can see which players are involved in the selected type of off-ball movement. They can also compare the performance of different players via bar charts. To understand why some players can perform well in the same type of off-ball movement, users can turn to the explanation view, which displays the keyframes from the off-ball moving process. The Voronoi-based visualization shows the game situations at a specific time. Furthermore, the vertically aligned diagrams reflect the situations of the 2 moving processes at similar times. Users can also compare the assessment results of the 2 moving processes through the bar charts and pie charts in the middle. We evaluated our system by conducting 2 case studies together with 4 domain experts. Let's see one of our cases.
In this case, Team New York Knicks is the least efficient when executing off-ball movements. To investigate Team New York Knicks' typical off-ball movement patterns, we click the row for further exploration. In the movement overview, there are 2 off-ball movements near the 3-point line in the top left corner. This means that the most frequent off-ball movements used by Team New York Knicks are very inefficient on offense. The histogram above the left-to-right baseline cut indicates the left-to-right baseline cut is often used when the score is close or in a big lead. Meanwhile, the histogram below suggests it is used more in the first half than in the second half of the game. In this case, the curl cut is clicked, as it shows up in the bottom left corner. In the player view, there are two interesting combinations of players. The combination of the number 2, number 42, and number 13 player ranks top and performs well in both the shooting expectation and passing probability. The combination of the number 2, number 7, and number 4 is ranked at the bottom. The cutter in both combinations was the number 2 player, Lanston Galloway. To investigate why the same cutter performs so differently in such a crow cut, users can turn to the explanation view. In this case, the cutter and the ball handler stand in almost the same positions at the beginning of the two off-ball moving processes. As the moving processes continued, the blue flow became gradually wider, and the yellow flow became gradually narrow. This implies that the first combination overtakes the second one in both the shooting expectation and passing probability during the movement. The Voronoi diagrams tell the reason. For the first combination, the screener has successfully blocked the cutter's defender, thus providing him with open space to receive the ball and shoot. As for the second combination, the screener has failed to block the defender. The differences in teamwork eventually led to a significant gap in the final scoring expectation of the cutters in the two processes. Therefore, Team New York Knicks needs to enhance the teamwork to improve their performance in off-ball offense.
In conclusion, we contribute an interpretive model, a visual analytics system, as well as expert interviews and lessons learned derived through the design study. In the future, we plan to adapt our assessment model to other team sports like soccer. We also consider how to balance interpretability and model performance, such as introducing deep learning methods to detect player roles. That concludes my presentation. I'm happy to take any questions. Thank you.
So welcome in the room. We have some virtual Q&A, and we already have some questions in Slido. So I would like to hand over the first question, which is your approach scalable to other sports where off-ball analysis is important as well?
Okay, that's a very interesting question. Based on some of my experiences, there are many common features between the two sports. For example, Voronoi chart is widely used in soccer analysis to model a team's defense. And we also take it in our system to represent the opponent's defense positions. Meanwhile, the controlling space is also a popular topic in both the soccer and basketball analysis. So based on these common features, I think after some modification, our system is able to help the soccer analysis.
Thank you. And another question, do you think your approach could be extended to also analyze on-ball movements? Understandable. Did you hear my question?
Okay, can you hear my voice?
Sorry, I didn't get it. Can you say it again? Okay, then we have to take the questions offline. So there is the opportunity to also discuss in Discord afterwards. We would like to thank you again for being here, and thanks for joining the session virtually. Thank you. So then we move on. The next talk is also going to be a virtual presentation. It's Visualization in Motion, a research agenda and 2 evaluations, presented by Lijie Yao.
Hello everyone, I'm Lijie Yao. I'm very happy to be here to present our work on visualization in motion. There are many scenarios that involve moving visualization, such as video games. Here you see bar charts attached to characters. Similar here for sports analytics. Sometimes it is the viewer who is moving. For example, a visitor needs to walk around to see all visualizations printed on the road. A more common scenario is both visualization and viewer are in motion, such as reading how many calories have been burned while running. All of these examples include what we call visualizations in motion. We define visualization in motion as visual data representations used in contexts that exhibit relative motion between a viewer and the entire visualization. We already showed several real examples of visualizations in motion, but what general groups exist? We classified visualizations in motion into 3 types. When the viewer is stationary while the visualization is moving, or when the viewer is in motion while the visualization is stationary, or when both viewer and visualization are moving. We propose that visualization in motion is an entire research direction. We already know very little about how effectively people can read visualization with simple motion, or with more complicated motion. However, in real-world examples, a lot of additional factors play a role, such as the predictability of motion, the contextual factors such as a busy background, or the change of camera perspective. In our paper, we discuss a research agenda containing these and many other challenges. Regarding motion characteristics, we first consider the moving speed. It indicates how quickly the relative position between viewer and visualization changes. The next one we call trajectory, which is the path of relative position change. Following is acceleration. It is the rate of change of speed. Next is the direction of motion, which indicates to where a reference space, a visualization seems to be moving. The second group of challenges concerns the spatial relationship between the viewer and the visualization. One example is viewing distance from a viewer to a visualization. It will affect the size at which a person sees a visualization. Other types of viewing changes appear when the viewers and the visualization's coordinate system change orientation relative to each other. For example, here a moving viewer focuses on a billboard containing visualizations. The viewing angle will change with continued movement. Finally, interesting effects can be studied regarding changes that happen between the viewer and the world space in which the visualization resides. For example, when soccer flies from one side to the other, viewer can see an arc in the air, while from the top, viewer will see a linear trajectory. When from the front view, viewer will perceive the size change in addition to the trajectory of motion. After talking about the motion factors and the spatial factors, now we turn to challenges related to visualization usage and design. First, we discuss the autonomy of motion. It means if the movement of visualization is independent or under human control. Another challenge relates to the predictability of motion. A predictable movement can come from motion with naturally predictable properties or from the direct control of a viewer. Following is the contextual factors, such as a clean background versus a noisy background. A chaotic context potentially noises viewers and reduces visualization's readability. Connection between visualization and its reference means how close the visualization is to its data reference. While visualization design properties such as representation, color, size, duration, and complexity define what a visualization looks like. The last aspect is technology that can be used to generate visualization in motion for different scenarios. Stationary screens such as a big display or a monitor are generally the most common place where a moving visualization can go. While microscreens such as mobile and wearable devices already carry visualizations with moving viewers. Instead, physicalizations generally involves moving viewers and stationary visualizations. Particularly, visualization in motion are common in augmented reality and virtual reality scenarios. Advanced techniques such as holographic projections, visualization by drones, or visualization embedded on robots might give a hand to let the visualization in motion more attainable. Now we are curious about how accurately can people read visualization under motion. We explored how speed and trajectory affect the readability. We conducted 2 evaluations on prolific. Our task was magnitude proportion estimation. We asked people to make a quick estimate from simple moving charts. For each evaluation, we tested donor charts and bar charts. Each chart contained 7 proportions. Each study had 60 participants. We had 3 speed conditions, a baseline at 0 speed, a slow speed at 15 cm per second, and a fast one at 30 cm per second. Our speeds came from a La Liga soccer match. The result of our evaluation shows, for both donor chart and bar chart, participants made more arrows at a higher speed. However, the absolute arrow differences between fast speed and baseline was less than 3 percentage points. That means, although speed has an impact, practically, this impact is weak. People can read helpful information from moving simple charts. Our participants performed slightly better on donor charts than on bar charts under all conditions. We had 4 trajectory conditions, the slow linear condition, and the fast linear one were our baseline, a slow irregular condition, and a fast irregular condition. Our trajectories also came from real soccer match. The result shows, for both donor chart and bar chart, no matter how fast the speed was, participants were less accurate on irregular trajectories rather than on the linear ones, especially at fast speed. Under the same speed, the absolute arrow differences between irregular trajectory and the linear trajectory was again less than 3 percentage points. Participants again performed slightly better on the donor chart than on the bar chart for all conditions. In summary, both speed and trajectory have an impact on the readability of moving simple charts. Higher speed and irregular trajectories generally lead to more arrows. The good news is, practically, people can read close to exact answers and got reliable information from moving simple charts. Since participants' performance was a little bit better on the donor chart might be considered before bar chart in design. To conclude, we first define what visualization in motion is. We then propose a first research agenda for visualization in motion. Lastly, we conducted 2 evaluations about how motion factors impact the readability. Our findings confirm a common sense that motion factors would affect readability, but we also provide that the impact is not that great. Our results offered opportunities to develop visualizations in motion for further research. Now I'm ready for questions.
Thank you for the presentation. Welcome to the room. We have a virtual Q&A session, and we have a question in Slido, which I would like to start with. That is, can you comment on the generalization of the study results from a wide background to a more complex and dynamic one?
Oh, could you hear me?
Yes, we can.
Could you hear me? Yes,
Yeah.
okay. So this is an interesting question. Thank you for the question from Zhu The generalization of the study results, yes, that's true. Our study was conducted in a pure background scenarios, but actually this is the fundamental research results that provide that people can perceive at least very close to the exact answer under this simple scenario. For a more complex scenario with more contextual factors such as a childhood background, etc., we have to move on and do more further research about it to take the fundamental results into a real application scenario, and that is what we are doing. Thank you.
Thank you very much. And another question I would like to ask is, Could you think of other visualizations or glyphs that might be helpful, like a slider or a gauge chart instead of donut and bar chart?
Oh, yes. Yes, the representations, we also consider it. Why we selected donut charts and the bar charts in our two evaluations, that is because our scenario is from the soccer match. A soccer match is a cycle. So we first selected a donut chart, and then we want to combine with another representation, visual representation. Thus, we added a bar chart as our between subject conditions. But of course, for the future research, we need to test it more representations. For example, a radio chart or a more complex visual charts to see if the visualization complexity would affect the readability and the usability for the visualization in motion. Thank you.
Thank you very much. Let's thank our speaker again. The next presentation is an on-site presentation. It's about interactive pattern mining of multivariate event sequences in racket sports. Presentation given by Yang Wu. Floor is yours.
Hello everyone, I'm Jian from Northwestern University. Today I'm pleased to introduce our paper, Recipe Interactive Pattern Mining of Multivariate Event Sequences in Racket Sports. I collaborated this work with my colleagues from Zhejiang University. And so players in racket sports like tennis and badminton prefer to use some tactics to win the game. For example, the video demonstrates a tennis tactic named serve and volley between Federer and Djokovic. And hit one, Federer served the ball to Djokovic's backhand area, and at hit two, Djokovic was forced to return the ball weakly with his backhand. And then Federer ran close to the net, hit the ball, and 1 point. So to help sports analysis fund such tactics, many data-driven tactic mining methods first characterize each hit by recording different hit features, such as ball position, hit tactic, and player pose. By applying pattern mining algorithm, such methods can filter out inconsistent or non-pattern hit features and discover the recurring patterns and tactics. So in doing so, domain experts have perspectives in interpreting player tactics. For example, if the player is a good server, experts may want to focus on the hit one and expect the algorithm to find relevant patterns, like particularly poses for serving. And on the other hand, if the player prefers net tactics, where the player hits a ball and a position close to the net, then the experts may focus on the hit three. So, however, current tactic data-driven tactic analysis cannot support such further interactive analysis with domain knowledge. So, and there exists two main challenges to support interactive analysis. First, experts may need to give fine-grained suggestions to the algorithm of a single hit feature. For example, experts might take a careful look at different hits, which depending on what tactic a player uses. And second, after the experts adjust details of the tactics given expert suggestions, the experts need to explore the adjusted tactics and judge whether the adjustment is reasonable, which is hard to achieve when the tactics are represented in a complex multivariate form. While prior work has studied different pattern mining algorithms, they have problems like pattern explosion, the lack of training data, and the lack of consideration of multivariate data. In addition, prior work on visual analytics for multivariate event sequences does not necessarily consider interactivity in pattern mining and evaluation. So to address these challenges, we collaborated with 5 domain experts in tennis, badminton, and table tennis. During our long-term collaboration over half a year, we summarized 5 analysis tasks about how to visually explore player tactics and how to suggest adjustment to machine-detected tactic patterns. So based on this task, we propose solutions through 3 steps. We first collaborate the potential expert suggestions and summarize the corresponding constraints and that each suggestion may impose in our algorithm. So to do so, we asked our domain experts to give suggestions on the tactics automatically mined from real-world sequences. These suggestions were classified into 9 tabs and translated into 9 corresponding constraints on our algorithm. These 9 constraints can be further divided into global and local constraints. The global constraints affect the entire tactic set, while the local constraints only require a fine-tuning of a few tactics and without changing other ones. For example, our system shows all tactics of Federer, and then experts may suggest focusing on Federer's serving tactics because his serve is known to be of high quality. And the suggestion will be mapped to a global constraint because it applies to the entire data. And next, experts may find that serving tactic 2 is actually a serve and volley tactic and suggest focusing on the ball position and hit 3. And this suggestion will be mapped into a global constraint, guiding our algorithm to adjust serving tactic 2 only. And our interactive pattern mining algorithm processes these constraints. And the core idea of our algorithm is straightforward. Given a set of raw sequences, a generator generates some candidate tactics, then an optimizer finds the best ones to construct a tactic set. And after domain experts see the tactic set, they can give suggestions which our system translates into global and local constraints. We have multiple generators and optimizers to handle those different constraints. Please refer to our paper for more details. And our NLP-based visual analytics system provides an interface to help domain experts interact with our algorithm. I will describe the core design and key functions of our system through a use case of tennis tactics analysis. Experts usually start an analysis from projection view that provide an overview of all tactics by a semantic-based scatter plot. We split the view into several sections to encode the most relevant hit features of a tactics. For example, the serve and volley tactic is most relevant to hit technique. Thus, it is projected to the corresponding section. And in the case, we can see that only a few tactics are about ball positions because our system initially moved many ball position tactics with low frequency. And the next is the tactic view. The core design and the core visual design of this view is a glyph design, where each hit feature is encoded by a glyph component. The opacity of each component indicates how many times the hit feature keeps the same value at each usage. In this example, we can see that the components encoding ball positions have low opacity, which means that the player usually changes the ball position while using these tactics. In the suggestion panel, experts can enter their suggestions in a natural language form. If an expert thinks that the ball positions are very important for the analysis, so they can enter pay more attention to the ball positions. And here we use a template-based NLP algorithm to translate suggestions to constraints. After such natural language-based adjustment, more tactics appear relevant to ball positions, and more components of ball position have high opacity. Thus, this adjustment satisfies the expectations of experts. So we evaluated our solutions through 2 quantitative experiments in terms of tactic quality, and runtime. The experiment's results show that it is necessary to include human adjustment to detect expected tactics effectively, and our system can effectively and efficiently support this task. And in our 2 case studies, 4 expert users found our solutions to be useful and intended task. So in conclusion, our contributions include a domain-centric constraint space, an interactive pattern mining algorithm, and an NLP-based visual analytics system. Future work may need to detect crucial but infrequent tactics and support easily searching tactic patterns. So thank you all for the listening. I'm happy to answer any questions.
Thank you for a talk. We're taking questions in Slido if you want to ask one. I will start with one, and it's about a little bit about generalization, because you used the ball shapes. Is it therefore hard to generalize the system to other sports?
You mean the glyph design?
Mm-hmm.
Okay. Yeah, I think we can have different glyph design for different kinds of sports, and they are sometimes thematically similarly. So, like if the badminton, we can change the shape from a ball to a shuttle, and then for basketball, it's also like the ball shape. Yeah. Thank you.
And the next question is, the glyphs are actually quite small in the visualization or in the application. Did that hinder the analysis? Was that difficult for the participants?
Sorry.
The glyphs are quite small in the application. Was it difficult for the participants to recognize them?
Yeah, I think that we can do some interactions, like when we hover a glyph and we then show more details about it, and we can also do amplify the interaction for the glyph design.
Mm-hmm. Thank you very much.
Thank you.
Let's thank our speaker again. The next talk is a virtual talk. It's about visual analytics system for IoT-based racket sports training. The talk is given by Yichen Wang.
Hi everyone, I am Jiachen Wang from Zhejiang University. I am going to introduce Tech Trainer, the visual analytics system for IoT-based racket sport training. Conventional knowledge-driven training method relies on coach's knowledge and experience, which can be biased in some conditions. To remove the biases, IoT-based data-driven methods are proposed. However, these methods are not friendly for coaches. Therefore, we integrate these 2 types of methods and propose an IoT plus visual analytics framework, Tech Trainer. Currently, IoT technology has been widely studied in sports training. Various devices have been introduced to collect trainees' detailed kinematic data during the training. Researchers use the data to investigate tasks such as action recognition and skill assessment. However, these studies cannot provide actionable insights for coaches. Besides, some commercial products are also released for users to collect and analyze the training process. However, these products only present basic statistical results. The fine-grained training data is not available for customized analysis. To facilitate the analysis of the motion data collected by sensors, researchers developed various visual analytics systems. These systems are used to analyze characteristics of motions of the upper extremity, brachial plexus injuries, and even the motions of horses. However, systems for visual analytics of the motion data in sports training are rarely studied. In the field of sports data visualization, considerable visual analytics systems are developed for the analysis of various sports, such as soccer, basketball, tennis, and table tennis. While these systems can help discover variable insights, they focus on the data of formal matches instead of the training process. Due to the difference of the data type and analysis goals, these systems cannot be extended to our scenario. Besides, several virtual reality systems are also developed for the training of table tennis. However, we want to solve problems in the real-world environment instead of the virtual environment. Therefore, we propose Tech Trainer. To construct Tech Trainer, we faced two challenges. The first is how to coordinate the sensor data and the information extracted by models for coaches. And the second is how to provide effective and efficient analysis for coaches. To solve the first challenge, we collaborate with 3 experts and summarize their requirements and considerations when analyzing the data collected by the IoT devices. With these considerations, we developed an IoT plus VA framework, Tech Trainer, which solved the second challenge. The framework consists of 4 components: device configuration, data interpretation, training optimization, and result visualization. Device configuration configures IoT devices for data collection. Data interpretation detects valid actions from the sensor data first, then it recognizes the technical attributes and estimates the performance indicators of the actions. Training optimization helps coaches assess the actions based on the results of data interpretation and generates optimization strategies for the poorly performed actions. Result visualization visualizes the process and the results of data interpretation and training optimization for coaches to analyze. In device configuration, we used 4 devices fixed on the racket, the right wrist, the right arm, and the left wrist, respectively. Each device contains a 9-axis gyroscope. The parameters of the devices are presented in the table below. Data interpretation is responsible for attribute recognition and indicator estimation. Before these 2 tasks, we need to detect and extract the sensor data of the stroke. We used the acceleration signals to detect strokes, since explicit peaks exist in all axes of these signals. We computed the energy of all signals and used conventional peak detection algorithms to detect the strokes. Then we trained 2 classifiers to recognize the technique and the position of each stroke based on the sensor data of each stroke. We tried many classifiers and the random forest performed the best among them. Finally, we used 2 regression models to estimate the speed and spin of each stroke. We also tried many models and similarly, random forest outperformed others. Therefore, we choose random forest for attribute recognition and indicator estimation. To be mentioned, to annotate the training data of speed and spin estimation, we drew special icons on the table tennis balls. We used the high-speed camera to capture the ball served by the ball machine. In such a manner, we annotated the specific values of the ball spin and speed. In training optimization, we first provide interactive methods to help coaches find the poorly performed strokes. We will introduce the interactions later. Then we generate the optimized suggestions for the poorly performed strokes. Here, we reconstructed trainees' movement trajectories. For example, the red line here presents the trajectory of the trainee's racket when hitting the poorly performed stroke. The blue line presents the optimized trajectory of the trainee's racket, which means if the trainee swings the racket in such a trajectory, he or she can improve the performance of this stroke. In such a way, we provide suggestions for trainees. In result visualization, we developed a visual analytics system to visualize all processes and results. The system contains 2 views. the training view, and the suggestion view. In the training view, each flow presents the complete training. We used the glyph to encode the stroke in the training. We used the metaphor of the dashboard to encode the speed and spin of the stroke. Besides, we referred previous work and encode the technique and position on the glyph. In the suggestion view, coaches can explore the trajectories of each optimization suggestion in 3D plots. Before analysis, coaches can use the system to record and visualize new training data. They need to first bind the sensors with trainees' drawings first. Then the system will record and visualize trainees' data in real time. Here, after the trainee hit the stroke, the glyph would exist in the training flow. After finishing the training, coaches can explore each stroke and move the slider to assess and find the bad strokes in the training view. Coaches can choose the bad stroke and click the optimization button in the suggestion view. In the suggestion list, coaches can choose the suggestion of interest to explore in the 3D view. That's all. Thank you.
Welcome to the room. We have a virtual Q&A session, and I would like to start with the first question, which is, did the devices, the additional devices, hinder the players in any way, or didn't they feel them at all?
Okay, thank you. It's a good question. Actually, the devices may influence the players' actions when they hit the stroke, but we have reduced the influence of the devices as possible as we can, but it is difficult to remove this influence. Actually, our system is applied to the process of training. So during the training, such influence is acceptable for coaches. And in the future, we hope we can develop more small, more tiny sensors that can reduce the influence of devices for trainees as possible as we can.
Thank you. And the question from Slido, very interesting work. I wonder how to apply the system to other sports.
And actually, if we want to apply the system to other sports, the two most important factors we need to consider is the attributes of the actions and the performance indicators to assess the actions. If we can identify such if we can identify the two factors, we can easily apply the system to other sports. For example, in soccer, maybe we want to assess the pass techniques of players. Then we can fix the sensors on the player's foot and collect their actions when they hit the ball, and maybe the indicators can be the flight of the ball and the length of the ball trajectory. And in such a manner, we can apply the system in soccer.
Thank you. There are some more questions in Slido. Maybe you would like to connect in Discord afterwards. Let's thank our speaker again. Thank you very much. We now move on to our last talk for today. It's the quest for omnioculars, embedded visualization for augmenting basketball game viewing experiences. And before we start with the talk, I have too much in my hand here. So This paper is a best paper honorable mention. And therefore, before we start with this talk, I would like to hand you the certificate in that case. Congratulations for that. All right, so the floor is yours. We are looking forward to your talk.
Yeah, good morning, everyone. Thank you so much for coming to my talk. My name is Tika Lin. I'm a PhD student at Harvard University. I want to first thank the Vis committee for the Honorable Mention Award, and also thank my wonderful collaborators and reviewers. So if you come to this talk because you are a Harry Potter fan, this slide is for you. Omniloculars is originally from Harry Potter. It is a magical object that provides you an ability to see everything about a Quidditch game, such as a play-by-play breakdown or a replay. Because you can see everything, we ask, why not data visualization? So we took the inspiration and studied the design of data visualization for a basketball game. As there are more and more live data available during a basketball game, fans are more engaged in the data analysis. However, it is unclear how to best present this data in-game to support fans' game understanding and engagement. Previous work has focused on designing visual analytics systems for expert analysts or journalists, but these systems are usually too complex for fans to use during a game. On the other hand, data provided on the TV are usually not sufficient. So if a fan wants to look up personalized or advanced data, they have to look up on the phone, which can be distracting during a live game. Therefore, there is a current gap in providing data to support fans in game data analysis. To tackle this problem, we present a design study on interactive game viewing with embedded visualization for basketball fans. We adopt a user-centered design approach throughout the study. We first conduct a formative study to understand what data do fans desire in a live basketball game. Next, we propose a design framework and build an omnilocular prototype to explore the design space of embedded visualizations in a live game. Finally, we conduct a user study to evaluate how well do embedded visualizations help fans understand the game and engage in the game. Let me first show you how a fan uses our omniloculars prototype to analyze a simulated game. I think the audio is not working.
I want to see shot label and team panel. It's so interesting to see the shot percentage climb up as they drive to the basket, show offense trajectory and defense form. This guy right here is wide open. And shot chart? Yeah, I can see J.R. Smith is having a good game. Height shot chart?
So I will share three aspects of our work. First, how we design these visualizations, how and why we build this simulated game environment, and how the user derived the game insights with omniloculars. So we start out by conducting a formative study with the actual basketball fans. We designed a contextual inquiry survey where we asked the fans to watch an NBA game and record the moment when they want to look up more data. For example, a casual fan wants to see the three-point shot percentage when he saw a player shoots many threes. We further interviewed 6 fans on their game viewing experience and walk them through an old game and record their think-aloud observation. In total, we collect 103 data-seeking moments from the fan. What we found was fans seek different data for different goals in different scenarios during a live game, which points to the importance of taking the game context into account when providing data in-game. So based on the results of these data-seeking moments, we derive a design framework for embedded visualizations based on game context. We categorize 3 components collectively form the game context, including scenario, task, and data. A simple example can be when draw MB failed, the user wants to identify the file number of MB. This context of data needs then drive the design of embedded visualization. Different visual components can be considered to encode different data. Next, in order to experiment and iterate on the embedded visualizations for a sports game, we build a simulated game environment. There are 2 reasons for this approach. First, because broadcasting companies usually don't share their original footage and camera configuration, it is a challenging computer vision problem to accurately track player position in the actual game video. On the other hand, designing the embedded visualizations require full control over the objects in the sports game, like the player or court position and viewing angle. Therefore, we create a simulated game in Unity to support our design exploration. We first establish the game setting based on the publicly available NBA player tracking data and 3D models. Then, because only 2D player positions are available in this player tracking data, we manually fine-tune the player and ball animations for the selected game clips based on the play-by-play data and actual videos. Finally, we combine different data sources to create visualizations. Here is a view of our simulated game. We simulate an old NBA game in 2015 between Warriors and Cavaliers, which was one of the most famous matchup in the recent NBA history. And because the viewer cannot tell the player identity from our player models, we show the game event description below the scene. So with this simulated game as a playground, we iterate on different embedded visualizations based on our design framework. We prioritize 5 representative game contexts based on 3 rounds of user testing. So we have 5 different visualizations with a focus on shooting, offense, defense, player performance, and team performance. Due to the time constraint, I will focus on the offense visualization. So offense trajectory helps fans identify players' movement through the trajectory and compare the player's open shot opportunity with this circle under the player. So the bigger the circle, the more open the player is. Finally, we conduct a user study with basketball fans to understand how users derive game insights with omnioculars. The study contains 2 parts. In part 1, the fans evaluate each of the 5 visualizations, and in part 2, they can combine different visualizations to help them generate game insights. We use the Wizard of the Art method to control the visualization. So the fans use oral command to activate different visualization, while the experimenter controls them in real time. In both parts, we collect the oral feedback and subjective rating. So let me share with you some of the key results. Based on the part 1, we found that fans found all 5 embedded visualization easy to understand, helpful, fun, and novel. Furthermore, each visualization provides helpful data on different game aspects. For example, with shot label, a fan observed, when I see LeBron drives, the color changed drastically, so I get that why he did not take the 3-pointers and try to make the drive. When using the entire system in part 2, users found it helpful and fun to use omnioculars. And moreover, most participants consider the insight they generate with this simulated game were comparable to an actual game. One interesting point I want to highlight is participants prefer different strategies to interact with these visualizations. Half of the people configure a fixed set. For example, a user chooses 3 different visualizations to help him focus on different game aspects and stick with them for the entire clip. The other half of users select a fixed set based on the game context. A user first uses offense and defense to understand the team drill, and then switch to using shot label to focus on the shot selection. In conclusion, we present the first design study on embedded visualizations for basketball in-game data analysis. We also propose a simulated game approach that enables highly accessible and controllable physical context to lower the barrier for situated visualization research. We also found that embedded visualization for live sports should be flexible and interactive to accommodate different user needs. For future work, we hope to explore beyond the screen game viewing experience with AR interaction. And for more detail, I invite you to look at the paper. And with that, I'd like to thank you for your attention and take questions.
Thank you for your talk. As a first question, I would like to take the one about the data you used. So what are the pros and cons of using game simulations instead of real game videos?
Yeah, so I think the pros is it's much simpler. You don't have the overhead to perform this computer vision algorithm to extract video. And the other benefit is because you have this entire 3D simulated game, you can experiment with different game viewing angle, or if you want to experiment different placement of this visualization, you are able to do so. So I think the cons is obviously it's not at a high fidelity, but based on our experiment, we also asked the user if they are able to extract game insights with our simulated game, and they were pretty much able to do so. So I think it's a trade-off, but in our scope, we want to focus on exploration of different design. So I think that served the purpose.
Thank you. Another question from Slido. Did the skew of the court impact the understandability of the game? And what are your ideas on perspective here?
Sorry, so the question is if the skew of the view impact the game understanding. So as far as I know, during our user study, the user did not have any problem with that. So I think because we construct the game in 3D, so that skew is because of the mapping to the 2D screen. So we conduct the user study over Zoom. So I think the next step would be we apply an AR or VR headset so the user can actually see the game in 3D. Yeah.
And I forgot to mention that the question started with amazing work. Last question. How do you think embedded visualization designs have to change when they are overlaid over a very busy background, like the fans or the game or something similar?
Yeah, I think that's a really, really interesting question. So in our study, we also found that based on the knowledge of different fans, some are more advanced, some are more casual fan, their information need is pretty different. So even though we only have one set of visualization for offense, for example, some people feel they can absorb information pretty easily and they make use of them, but some casual fan would think that's overwhelming and then they can only focus on one part. So in our paper, we also discuss like how this visualization design should consider different fans' needs, and by providing interaction or more flexible personalized setting, they can pick and choose what fits their needs the most.
Great, thank you very much. Let's thank our speaker and all the speakers again. There are some more questions in Slido, or maybe you wanted to connect in Discord afterwards. And this closes the session. Thanks very much for joining, and now it's time for lunch. Thank you.